point. Is this the pointer?
There is no pointer, I think.
That's all right. I'll, yeah, okay, that's fine. Okay. Great. So I'm going to talk about some recent work that was done at ECMWF, where we've been, where recently our forecast went from being uncoupled atmosphere only forecasts to being coupled. So there's a few different contributions from different people at ECMWF. And so we've known for a long time that that coupling was really sort of fundamental for climate prediction. So the early sort of papers by Manabe and others in the 70s and 80s was known that the impacts of changes in sea ice were incredibly important for changes in temperature in a warming climate. But it's been sort of less of a focus for NWP at the sort of forecasting for sort of daily and weekly timescales. But just looking at an image like this, you can see that it's very important. So this is showing a sort of cold air outbreak event across the sea ice, and you can see the formation of these really sort of beautiful cloud streets, and the sort of interactions that sort of at the ice edge where you've got the sort of the topography and the sort of the openings there sort of really sort of corresponding with where the clouds start. And so until recently, NWP systems were had sort of thermodynamic representation of ice only, so they were sort of persisting the sea ice cover itself. But we've got sort of evidence from modeling studies and sort of from theory that actually it's very, very important for development of boundary layer downstream of the sea ice edge. And so having sort of a dynamic representation of this is thought to be really important. And there's been a lot of work in recent years at ECMWF, in Canada, and the Met Office in the UK to sort of develop coupled systems. And so this set of experiments, we're looking at we're sort of comparing what we were doing in operations before to what we're doing in operations now. And so we've got an uncoupled run with persisted SSTs and sea ice, and then a coupled run where the forecasts are where the sea ice is allowed to evolve dynamically, and then one in the middle where we have observed sea ice and SSTs, but they're updated through the forecast rather than just persisted. And you can see from this graph quite clearly why persistence is a sort of a poor approximation. So this is showing the time series of sea ice extent in the Nordic seas in black here, and then we've got in blue is showing the sort of the old uncoupled forecasts at ECMWF, and you can see that sometimes persistence is okay. But when we've got very rapid changes in the sea ice edge, it's actually a very sort of poor, it can be a very poor approximation indeed. And the sort of the orange and forecast are showing the coupled model. And you can see that it does a much better job of capturing the observed evolution. And so one of the scoring methods for which is probably most important for so the ice edge is probably one of the most important features from a meteorological perspective. And so we're evaluating this using this integrated ice edge error metric, where you sort of sum over the areas where they're mismatched, so where there's too much ice or there's too little ice. We just sort of sum that up and we get a measure of the integrated ice edge error. And then this is the lead time perspective for that same region I was showing before. And the blue is showing the uncoupled persisted sea ice, which obviously gets quite the areas grow over time quite rapidly. And then in the coupled forecasting system, I mean, this is showing us that it's at all lead times it's more skillful. So the dynamic, allowing the sea ice to evolve dynamically, is always improving the position of the sea ice edge. But unfortunately, it's not doesn't look as good as this everywhere. So this is a region, sort of the region of the North Atlantic around Greenland, and you can see that particularly in the early part of this, there's an overestimation of the sea ice cover, and this gets worse with lead time. And then later on, as we get into March, there's a sort of an underestimation of the sea ice. So we've kind of got this these biases which seem to be changing over time. And then this is kind of what you don't really like to see, is that, you know, the orange curve here is larger, so the ice edge error is larger, basically at all lead times, compared to a persistence forecast. And interestingly, so I'm showing the red line here. This is the error in the ocean analysis, showing that actually much of the error is coming from coming from the initial analysis that we're using to initialize the forecast. Okay, and so if we, you know, so we can ask the question, you know, are these improvements coming in all forecasts or just in some? And what we can do is we can look at things like the 3-day change in the sea ice extent, and then the change in the day 3 forecast error. This is what's plotted here. And you can see from this sort of slightly horseshoe shape of this scatter plot that actually the forecasts are most improved during periods where the sea ice extent is changing most rapidly. And so the Nordics, and this is the same in both of the regions that I showed. And so even in the Labrador and and this section of the North Atlantic, in the sort of Labrador and Baffin Bay regions, where the forecasts on general are worse, the dynamic sea ice model is actually, when the sea ice is changing really rapidly, it's still doing a better job than a persistence forecast. And then we can sort of dig into this a little bit more. So looking at this sort of three-day changes in the sea ice edge during sort of periods of ice advance and ice retreat. And we can see, so we're compositing over these sort of cases of ice advance and ice in the top line and ice retreat in the bottom line. And we say that even though the sea ice model is getting the pattern of this right, so it's kind of the change is a little bit sluggish. So there's potentially still some work to be done to get the dynamics correct. But what about the atmosphere? So I showed this picture before, and we think that there's particular sort of situations like this where when you've got sort of a cold sort of polar air mass coming across the sea ice edge, you know, you've got a very strong sort of thermal gradient between the ocean and the atmosphere. And, you know, in particular, like the sort of the position of the sea ice edge as the sort of leading edge where this sort of transition between these two regions occurs is quite important in terms of how this sort of the boundary layer develops. And if you're not representing this, the sort of the change in the sort of rapid change in the sea ice edge that you get during conditions like this, then you might sort of be introducing an error. And we've looked at this in the situation where we've got a persistence forecast of the sea ice. So you can see this in the top left. So we're always underestimating the sea ice during these conditions because in reality the sea ice is advancing, but it's not allowed to change. And it does end up, and the errors in the fluxes that you get associated with this do lead to a warm bias in the atmosphere. And you can see that when we've got the sea ice is allowed to evolve, both in where we're using observed SSTs, and when we're coupling to the ocean, that actually the sea ice is better, and it's also and we're actually getting a lot of a sort of a cooling compared to the control forecast as the turbulent fluxes are improved. Okay, so in terms of conclusions, dynamic sea ice has the potential to improve sea ice evolution and atmospheric fields in the medium range, particularly during cold air outbreaks. But it also has the potential to degrade both the sea ice and the atmosphere too, due to sort of biases or errors that are introduced in the forecast. And in this situation, the coupling improves the ice edge error significantly overall. But we do have these sort of slightly tricky regions where it does sort of increase temperature and humidity biases. But we think a lot of this is due to systematic errors in the ocean analysis, partly related to the fact that the minimization for the sea ice concentration is sort of done sort of in isolation rather than in conjunction with the SSTs. So and the mixed layer temperatures, so you sort of get some inconsistencies there, which mean that the sea ice grows back a little bit too quickly when it is removed. And the sort of the subjective evaluation against the MODIS data that I included in there sort of suggests that this is really that the biases with respect to OCSAF near Greenland are real biases rather than just sort of differences in different analysis products. Okay, thank you.
So thank you, Johnny. So we have time for questions.
Hi. So have you considered the bias of OCSAF near Greenland? Because near the coast, the OCSAF doesn't see sea ice due to land contamination. And if you look at the southeastern part of Greenland, that's more or less removes all the ice.
Oh, I can't get back to the slides. Is it possible to get the slide back this time? All right, I've got. Yeah. I mean, so this is. Oh yeah, there we go. So just to explain the bits that I'm talking about. So the Ocean 5 analysis, the ice edge from that one is in green here. And then the OCSAF is in for the same day is in blue, and you can see that there are these sort of areas of disagreement. So you've got this region. It's basically this region there's one region on the east coast and then one region on the west coast, and then you've got this sort of long strip on the east coast, which I think is. So I think those are the two sort of areas there. And I think the fact that there's, I mean, I think it's obviously right when you say that there are issues like near sort of orography with those products, but I think you can sort of, it looks quite clear on this. I mean, those are the areas where there are the differences that are causing this change in the error. I mean, I guess I don't know if anybody knows whether that's sort of a spurious difference or whether that's a real one. But I think, based on the MODIS picture, it looks like it's fairly robust to me.
More question? Behind?
Hey Johnny, great talk. I was wondering when you mentioned that the model was too sluggish, kind of bringing that sea ice edge, or moving that sea ice edge. Did you compare the sea ice motion in the model and in observations?
No, but I think that would be really nice to do. And as we were sort of talking about, it'd be nice to sort of see whether or not is it due to the fact that there's an error in the ice thickness, which is, which means that even given the right wind forcing and the right, reasonable roughness, you're not getting the right sort of dynamics, or is there something else going on there?
Okay, thank you.